Hello, so today we will be looking at exponential modeling. Now we looked at linear modeling in section 8, and it is important that we look at its alternative, which is exponential modeling. Now this video is going to be in two parts. So I intend making the first part of this video from pages 107 to pages 116 of your test. Okay, so we are on pages 107 of your test, and let's get the discussion going. All right, so not every situation can be modeled linearly. So we recall compound interest is an exponential relationship where money grows increasingly over time. Now let's consider some other applications of this mathematical tool. All right, so we've been looking, so far we were looking at y is equal to mx plus b, and this is what we call the linear model. Now we want to look at what exponential modeling is, and we'll look at the relationship between absolute and relative change to linear and exponential model, and we'll look at how to find the growth factor. All right, now as part of this, we'll also explore simple and compound interest. And I want to ask the question, if you wanted to go for a loan, would you choose a simple interest loan or you choose a compound interest loan? And if you want to go for an investment, will you choose a simple interest or a compound interest? All right, now I'll let you know before the end of this section. Okay, so let's get the discussions going. All right, now we want to consider the following situation for Oliver, who opens a retirement account by depositing $1,800 in the initial year. He intends to increase his deposit by $100 each subsequent year. Now, how much does Oliver expect to deposit in year 1 and year 2? All right, so if his initial deposit was $1,800, at the end of year 1, he should have $1,900. And year 2, he should have what? $2,000. All right. Now we want to put this on a table. All right. Now we want to use the table below to chart the expected amount of Oliver's deposits by year. Now we want to calculate the absolute and relative change. So you realize that, don't forget that absolute change is the new minus the old. So here, to find the absolute change right here, we will do the new minus the old. So 1900 minus 1800. So we realize that absolute change stays constant. Okay, now we want to find the relative change, which is the new minus the old all over the old. Okay, and we realize that that differs, right? It does not stay the same. Now, let's answer the following questions under the table. How are the amounts of the deposits changing from year to year? And you realize that they change by adding $100 each year, okay? Now, which value stays the same, the absolute or the relative change? And quite obviously, absolute change stays the same. And now, without continuing the table, how can you mathematically find the amount of Oliver's retirement contribution in the 6th year? Okay, does this give you some idea? So the initial, so you realize that you have to take 100 times 600 plus 800. And does this look familiar? All right, and this looks like what? A linear model. So we have y is equal to mx plus your b. So the b is the constant, has initial deposit, and the deposits are changing by what? 100. So 100 is our slope, okay? So what kind of model is this? And I'm sure you already said that this is a linear model, okay? Sweet. Now, this is the key. When absolute change is the same from time period to time period, the mathematical model is linear. Okay, the slope or rate of change is the absolute change, and the y-intercept is the initial value. Is that okay? So when you have absolute change staying the same, the model is a linear model. And we are going to realize very soon that when relative change stays the same, we have an exponential model. Now, let's try another strategy. If Oliver increases his deposits by a percentage each year rather than a specific dollar amount, okay, from our previous scenario, Oliver realizes that $100 is roughly 6% of his contribution. He decides to increase his deposits by 6% in the coming year, okay, then increases that by 6% in the following year, and so on. Now, if Oliver increases his deposits by 6% in the first year, how much will Oliver deposit by the end of the first year? And that will be what? $19.08. And this is how this happened. So because that is an increase, what do? You have to add that to 100. Is that okay? And you multiply by the initial deposit. So this becomes 106 over 100 multiplied by 1800. And that is why we have 1.06 multiplying 1800. And that comes out as 1908. Is that okay? So that is at the end of the first year. Now, the second year, we are going to do 1.06 multiplied by that. And let's put that on the table. So look at it. So here you do that. Okay, so you do is increasing by 1.06. So to find the second year, we have to multiply this amount by 1.06. To find the third year, we have to multiply this amount by 1.06. And it goes on and on and on. Is that okay? So that is how this happens. And what do you see? Now you realize that absolute change has varied and now relative change stays the same. Okay, so we go back to our conclusion. We draw the conclusion that now how are the total of the deposits changing from year to year? And you realize that increasing by 6%, okay, by multiplying each year by 1.06. Now what value stays the same? The relative change stays the same, okay? And to find, without continuing the table, how can you mathematically find the amount of deposits in the sixth year? So here, you just do 1.06, 1.06, 6 times, okay, multiplied by the initial amount. And that can be simplified as 1800, okay, 1.06 exponent 6, and that will give you that, okay? And that is what we call an exponential model. Okay, so when relative change stays the same from time period to time period, we say that we have an exponential model. Is that okay? Nice. So this is the formula for an exponential model. The amount is equal to the initial amount, the growth factor, and then the time period. Okay. Now, one way to find the growth factor is to use the following formula. Now, I also mentioned that the remaining sections, chapters will actually be more formula work. So if you go, there's a yellow sheet right at the center of your book, pages 2, 3, 6. You'll find these formulas there, okay? And we are going to use these formulas. So the growth factor is 1 plus the percentage increase. And that is why we used that to find Oliver's increment, 1 plus the percentage change, okay? And this is 1 plus because we did 100 plus the percentage change of what? 6%. And percent means what? Out of 100. So we had to do 106 over 100. Okay, and that gave us 1.06. Is that okay? Nice. Now, there's another formula that will be used, and we will look at that as well, how you can use that when you have consecutive numbers to find the relative change. Now, use 1 plus that to find the growth factor for the donations, and that is what we did, okay? Now, the growth factor can also be found when you don't have the percentage, but you have consecutive numbers. You can use the new value over the old to find the growth factor, and we shall look at examples of that, how you can use that to find the growth factor, okay? Now, use consecutive values to find the growth factor, and these are values that are coming from the table we looked at earlier on Oliver's investment, increasing by 6% every year, all right? And it's the new over the old, and that still gave us the same answer, okay? Now that having a relative change of that increases a growth factor, all different ways stating the same relationship, okay? Now, in the retirement deposit example, the initial amount is 1,800 and the yearly growth factor is what, 1.06. Now, to find the expected donations after 6 years, you have to do 1,800 times the growth factor and to the T, and the time is what, 6 years, and that gave us that outcome. So here, this is a graph that compares the linear model versus the exponential model for Oliver's investment. So when Oliver, so here, if you look at this graph, the blue one shows the linear model, and this shows the exponential model. Which of these will you go for an investment? And you realize that the exponential model yields more. Is that okay? So here, we want to look at the difference between the two, and the exponential model is 8,500 more by increasing 6% rather than adding 100. Okay, so for an investment, an exponential model is more appropriate because that yields more money. Okay, now here we wanted to look at, estimate how much each deposit will be in 35 years for both of the investment, the linear versus the exponential. And that is what you have. So we just had to divide, we broke them up into 26 equal deposits. So we had to divide the return at the end of the period, 35 years, by 26 months. And that gave us the monthly payments. Okay. Now, let's look at some examples. Okay. Some practical situations. Are you ready? Okay, let's go. Now, this is an example that says, according to the UN, in the year 2000, the world population was approximately 6.2 billion. We want to respond to the following, assuming the population has grown by 1% per year. The first question, what is the growth factor? What is the growth factor? What is the growth factor? Okay, so we are going to refer to the formulas, the formula on pages 108. So the growth factor, okay, we know is 1 plus the percentage increase. Okay, so what is the percentage increase, which is 1%? So we have to change 1% to a decimal. And to change 1% to a decimal, just do 1 divided by 100, and that is 0.01. So the growth factor is what? 1.01. Gucci? All right. Now, what unit is time measured in? And time is measured here in what? In years. Now, what is the exponential equation for the world population using the population in 2000 as the starting point? Okay, so the exponential equation, don't forget, the amount is equal to the initial, okay, and that formula is also on pages 108. The growth factor, I'll call it the GF to the T. The initial is giving us 6.2 billion, right? The growth factor, we just found that as that. And we don't know the time, so we put T. And that is our formula. Okay? Is that okay? Sweet. Now, estimate the world population for 2014. 2014. So here, what do you do? What do you think? So for 2014, the starting year was this for the UN in 2000. So if you want to estimate the population for 2014, what do? You have to make sure you find the year difference. So 2014, between 2000 and 2014 is 14 years. So you plug that in for your T over here. Okay, so 6.2. So the amount will be equal to 6.2. Okay, 1.01. Okay, exponent 14. And that should give you the estimated population for the year 2014. Is that okay? Nice. Now, let's take another example. Okay. Wade found a rare Masters of the Universe action figure set in a box for his childhood toys. He's been tracking the price of a similar set online to monitor the rising value of his own collection. We want to use a table of values to address the following. So this is a table of values. So the starting year, okay, Wade started from 2014 and he's tracking the values. So here, we want to use two consecutive numbers, values, to find the growth factor. And we mentioned that, and that formula is on pages 109, where we said the growth factor can also be found when you do not know the percentage increase. You can find the growth factor using the formula, the new over the old. Have you seen that on 109? The new over the old. So between 2014 and 2015, the new over the old. So 2015 is our new, and the value for 2014 is our old. Okay. You can also check if you want to use 2016 and 2015, your growth factor is going to be, and you get the same value, 271.63 over 248.68. Either of these will give you the growth factor. Okay, check that. So you use this formula when you do not have the percentage increase, but you have consecutive numbers, okay? And either way, you get the answer. Now, what is the unit of time? Which is years, right? And assuming this trend continues, we want to estimate what the price would be today. So today, we are in the year 2020. So we are in 2020. And if you want to estimate the price for today, the starting year is what? 2014. So you strike the difference to 2020 minus 2014, which is what? 6. So our T is going to be what? 6. So we know the amount is equal to the initial, and the initial value for 2014, which is 227.67. We found the growth factor to be 1.09, exponent what? 6. And that will give us the price for 2020. Gucci. Makes sense, right? Excellent. So when you're asked to estimate the price for a projected year, what you have to do is you have to find the year difference, okay? And that becomes the value of your T, and you put it as your exponent. Okay, nice. Now, we have established a while ago that when absolute change stays the same, we have what? A linear model. And when relative change stays the same, we have an exponential model. So this table, we want to use this table, which growth pattern, to identify which growth pattern is exponential. So right away, we have to look for what? The relative change. So we have to check for future, classic, and standard. We have to find the relative change for each of them. So the one that happens to have the same relative change will have an exponential growth. So I'm going to pop this table up. So I did this and relative change for each of them, and realize that the relative change for standard stays the same. So we say that standard has a standard increase of 150%. So it is the exponential model. Okay. So this is coming from the fact that we have established that when relative change stays the same, we have what? An exponential model. So standard has an exponential model. As simple as that, period. Okay, awesome. Can we go to the next? Right. Now, it is also very important, and here we're going to discover that whatever goes up comes down. Okay, now what goes up must come down. When something is growing, but say dying, when something is not growing, but say dying off, losing its effectiveness or decreasing at certain intervals, we call that exponential decay. So far we've been looking at exponential growth. Now the opposite of exponential growth is what? Exponential decay. And I'm going to let you know that each of you at one point or the other has experienced exponential decay before. Okay, when you take a medication, say you take Tylenol, 500 milligrams, with time, that decreases in your system. All right, that is why when you go to the hospital, they give you a medication, they give you a number of hours intervals to take that medication. All right, so it breaks down. The potency of the medication keeps breaking down, and you have to take another to replenish the potency of that medication. All right, the same thing happens when you take alcohol. Okay, it goes through exponential decay, or any other substance. Is that okay? Nice. So let's get into exponential decay and see some interesting examples. Right. So really the formula here doesn't change much between exponential growth and exponential decay. Is that okay? So we're still going by the amount is equal to the initial, but instead of growth factor, we replace the growth factor by the decay factor and the time t. Is that okay? So, sweet. Since the item in question is shrinking over time, the percentage change is subtracted from 100. So, whereas we add to 100% in growth, we subtract from 100% in decay. Is that okay? And that is written like that. Now, decay factor can also be found by taking the ratio of two consecutive numbers. So, just as we did in exponential growth, when we know the consecutive numbers, we can use consecutive numbers to find the decay factor. Okay, nice. Example number 1. Airline miles have a tendency to lose value over time as airline companies change or update policies. Alicia traveled often for business and had earned 500,000 frequent flyer miles prior to her retirement. She estimates that her miles lose around 26% of their value from year to year. Now, the first question. What is the decay factor? What is the decay factor? Can you go to pages 111 and choose which formula to use? So here, the percentage decrease has been given. All right. And don't forget that the decay factor, I'll call it DF, is 1 minus the percentage decrease. And don't forget to change that. So 26% over 100. Change that to a decimal. Okay. And this is 1 minus 0.26. And what would this give you? 1 minus 0.26. Work that out. And that gives you what? 0.74. So you have found the decay factor as 0.74. Is that okay? Gucci, Gucci. Nice. Now B, what is the unit of time? And that is years, right? Now construct an exponential model to approximate the value of her airline miles for any given year. Construct that, and you will find the same thing, the same formula on pages 111. So the amount is equal to the initial, and what's the initial? 500,000. Okay. And your decay factor is already there. And because you are going to use this to estimate for any time t, so you put that as your formula, and that is it. Okay, so the amount is that. Now, how many miles will remain 5 years after Alicia retires? So now you plug in 5 for what? For your t, and that gives you 110,950 miles. Does this make sense? Awesome. Nice. Now, let's look at this. And this is the example I gave at the beginning, right? So, exponential decay model comparing antibiotics. Is that okay? So right here on this table, we have hours since last dose, and then we have doxycycline, and we have amoxicillin. Is that okay? So the initial dosage for doxycycline is 100, and the initial dosage for amoxicillin is 500 mg. Now, what do you see? You realize that it decreases as the hours increase. So when you take it, the potency of the medication keeps dwindling, right? It keeps going down. So here, what is the recommended dosage for amoxicillin? The recommended dosage for amoxicillin, and how do you find that? And that is right there, right? 500 mg at time 0. So that is the recommended dosage for amoxicillin. Okay, good. What is the recommended dosage for doxycycline? And doxycycline is 100 milligrams because that is the starting dosage. How much does amoxicillin degrade from hour to hour? And what is the decay factor? Look at it, amoxicillin. So it starts at 50, right? And then it breaks down. By the hour, it's broken down to 250. Isn't that half? Okay, so half. So decay factor is 1 minus 0.5, and that is still 0.5. Okay. Now look at doxycycline, and what is happening? 30% decay, and that is 1 minus 0.3. Okay, and that is what? 70.70. So you can as well use the new over the old to find the decay factor, right? So for amoxicillin, if you decided to use 250 divided by 500, that will give you 0.5. For doxycycline, if you decided to do 70 divided by 100 will give you what? 0.7. And that is very interesting. So the exponential decay equation for amoxicillin is the initial 500 times the decay factor to the T. And let's look at doxycycline as well. And that is 100, which is the initial, multiplied by 0.7 to the T. So we see that the medications lose their effectiveness over time. Now, would it be acceptable to come up with a medication that once taken would remain active indefinitely? Certainly no. We don't want to be medicated indefinitely. Worry about side effects. Okay? Nice. Okay? So take a breather, reflect over what you've done so far, and you realize that this is really very important for you to understand this concept. Is that okay? Now, here are some more situations we can think through, right? So the graphic below, we're going to use the graphic below to answer the following questions. So this is days since discovery. We have new life form and number of life forms. And we are going to see a trend. This is the graph and see what is happening. We're going to use that to do some analysis. How are the number of life forms changing from year to year? Okay, so if you do the ratio, the new over the old, 80 over 40 gives you what? 160, which is the new over the old. New over the old. And which is what? 80. So what will you say? This is a doubling situation, right? It's doubling. Now, what is the initial value? At 0 is what? 40. Okay. Now, can you put these together? And what is the unit of time before days, right? Now, if you want to construct a model, we know the amount is equal to the initial, the growth factor to the T. And the growth factor, we had that to be 2, right? So that is the formula. And now, here, we want to use guess and check to determine when the number of life forms will reach 2,000. So what we're going to do right here is Y now, we know the amount to be 2,000. Okay? So we want to know when the number of life forms will reach 2,000. So we just have to keep on varying, changing the T until we get a number 2,000 or a little more. Is that okay? Now, we could have used logarithms to do that, but logarithms should not be covered under this. So we have to use guess and check. We have to keep changing the T, okay, until we get 2,000. And you realize that when T is 6, we will have 2560. When T is 5, you have something less than 2,000, so that wouldn't be right, and we want whole numbers. So now 6 is the value for our T. So T here will be 6. So that is why we call it guess and check. So you have to vary the T until you get a number 2,000 and a little more. Okay, nice. And we're going to use these same applications, okay, to work on the decreasing rate of appliances, okay, or stuff. High definition TVs are averaging 1,500 currently, but costs are decreasing at a rate of 15% per year. In this case of exponential, is this a case of exponential growth or decay? The costs are decreasing. So this is what? Decay. Now construct a model. So we know the initial, is that okay? And we should know the decay factor. And the decay factor will be 1 minus 0.15. Okay? So we found the decay factor to be 1 minus, we changed the 15% to a decimal, which is 0.15, and that gave us 0.85, and that is our decay factor. Okay, so you plug it into the formula. The amount is equal to the initial, which is 1,500, and the decay factor of 0.85 to the T, and that gives you this expression. Okay, now how many years will it take for these TVs to be half of their original price? So the starting value is what? 1,500. Half of that will be what? The 750. So now what do? You put 750 right there, and you have 1,500.85. And you want to vary your t. You want to keep changing your t. So the time until you get 750, and it will be what? 5 years. So if you put 5 there, that should give you the answer. Guess and check. Okay, you have to just keep varying your t until you get the answer, and that is how you get that result. Okay, nice. A car, a 22,000 car depreciates by 15% per year. Okay, this is a case of what? Decay. Determine the model, and we did the decay factor by doing 1 minus, you change the percent to a decimal, and that gives you 0.88. You plug that into the formula. So now your T is what? 4. So in 4 years, the car will be worth that much. Okay. And Michael has recently opened a savings account. The banker gave him an equation to predict a balance at any given month. So this is M, and this should tell you that this is a growth, right? What is in parentheses should tell you this is the growth, and this is how much Michael starts with. Okay, so how much did Michael deposit? And is this a case of growth or exponential? That is growth, right? And what is the monthly interest? Okay, and what is the account balance after 6 months? So now, after 6 months, you plug in 6 right there to find the value after 6 months. And after 12 months, you plug in 12. Okay? And that is as simple as that. Gucci, Gucci. All right. So you just have to know when this is a decay scenario and when this is what? A growth scenario. And then you apply the formulas appropriately. Is that okay? So that's all you have to know. After reading the problem, you ask yourself, is this a decay situation or a growth situation? All right, and then you choose the right formulas. And like I've told you, the yellow sheet on pages 235 and 236 will come in handy, and those will be, you will use those when you're taking a test. Okay, so really, you don't have to memorize the formulas. You just need to know when to use these formulas. Okay, so thank you very much, and I'll do the second video to finish this section where we talk about the peasant and the king. A very interesting story about exponential growth and exponential decay, or relating linear and what? Exponential. Okay, so I will see you, and thanks. Have a good time. Bye.